Well, hello again. In this example, you will learn how to take the internal moments found by the moment distribution method and use those to generate shear and moment diagrams. We're going to look at this particular beam, and what has been provided for you here are the moments as if we had run the moment distribution method. So these are the final moments that we would have come up with. What we're being asked to do is take these results, which by the way are reported in the sign convention that we use for moment distribution, and then plot the shear and moment diagrams for this beam. So this is going to involve some statics, but we need to make sure we understand what the sign convention is for moment distribution. That sign convention is that moments that are clockwise are positive. Eventually we're going to have to translate this over to what we call beam sign convention. So if we had a member here, beam sign convention is that shears will cause a clockwise rotation of a member, and moments will point to the top. So we've got to do a sign convention translation. We're going from this to this. We'll show you how we handle this as we move forward. You need to be aware of the numbers that are going on here. And the process I follow for this is I go ahead and begin sketching the free body diagram for each of the individual members. We know that at point A we have a zero moment. We can get that from the table here. We know at the end of member BA it's 115. Look, that says it's a positive, which means that it rotates clockwise. So let's go ahead and get that sketched in here. Now one of the things you're going to notice is as I'm sketching these arrows on here, I will not put signs on them. I am simply using the signs in this moment distribution table to help me identify which direction I should be sketching the moment arrow. So for BC, it says it's a negative 115.87. Since it's negative, that means it's rotating counterclockwise. I come back here, that'll be 115.9. Let's go ahead and get the moments at C. So that's 326.81. So I can come back here using the translation of the sign convention, 326.8 and 326.8. So those are the moments that I know. Now I know that at the end of each of these there should be a shear, so I will assume, using positive sign convention, shear at A, and then shear at B. Shear at B, shear at C, always using positive sign convention, shear at C, shear at D. One thing I need to make sure that you completely understand is that when I'm writing this V of B and this V of B, those are not the same magnitude. If you need to make it clear in your own mind, this is V of B to the left of joint B, shear at the right of joint B, and so forth. And the same thing goes on for the shear at C. Those are very different values. What we would need to do from this point is we would go back to member AB, and we would start running equilibrium to solve for what those unknown shears are. So I would take the summation of moments at A, and what that would solve for me is it would find VB. Now I'm not going to write out the equilibrium equations. If you need to verify it, you can do that. But what I would find is that it computes out to be a negative 18.86. Then the next equilibrium equation I would run is summation of forces in the Y, and that would compute out for me VA. If I did that, the value I would come up with is 11.14. This next one, I would sum moments about point B. That would get me the shear at C, and that would compute out to be negative 50.55. And then I would sum forces in the Y, and that would solve for that V of B, which I would compute out to be 29.45. All of these being units of kips. And then lastly, if I would sum moments about point C, that would get me the shear at D. If I would sum forces at Y, that would get me the shear at C. And these are the values that it would compute out to be negative 49.11, and shear at C is positive 70.89. This is the most critical part of the entire process, getting the moments moved from the moment distribution table onto your free body diagrams, and then using equilibrium to solve for what your unknown shears are for each of the individual members. Do not short circuit that process. You need the free body diagrams. Then from here, we can go ahead and construct the shear and moment diagrams. And what I want you to do is I want you to just think of each of these as being a separate member. Generate the shear and moment diagram for each of those independently. So this is what I'm going to do. You should know how to generate shear and moment diagrams proficiently at this point. So I'm simply going to begin sketching these up here. 11.14, negative 18.86. And if we were to come back through, we know we've got a point load here, which provides a discontinuity. With a point load, it would develop me a shear diagram that looks like this, which if I were to calculate areas under those, this would be 167.1, and that one would be negative 282.9. Now, because I want you to think of these as being separate little beams, let's go on to the moment diagram before we go on to segment BC. So the moment diagram that we would get assembled, we'd have a 0 moment here and a negative 115.9 here. Going back to the left, working from left to right, this will be 167.1 due to that. And then we have a change, negative 282.9, which would actually bring me back to here. Okay, so I essentially just treated that as its own little beam. Now what I want to do is let's do this one next. 29.45, negative 50.55. Since it's a distributed load, that would be a first order curve. Just trying to get some of these basic dimensions here. This is 7.36. And this dimension here is 12.64. And then you can get the areas of those. Area here would be 108.4. Area here would be negative 319.5. Let's go ahead and project down that discontinuity as it comes down here. Looking back here at this, we see 115.9, negative 326.8. So those will be the two values that get plotted at the end. So negative 326.8 and the negative 115.9, we've already got that going on there. So from 115.9, move up a total of 108.4. That'll give me a value up here that computes out to be negative 7.5. And then it's going to drop me back down to that 326.8. It'll give me a second order line because it was that distributed load. And so now we've got that portion of the moment diagram done. Lastly, let's go to segment CD. You got 326.8, 70.89, negative 49.11. I can get that shear diagram going on, which give me the 70.89. And at the other end, negative 49.11, being a distributed load. Make it a linear here. And got 17.72, 12.28. We can get the areas. So area here, 628.1, and area here is negative 301.5. Get the discontinuity projected down. Plot the moments at each end. So at the far left, it's 326.8. At the far right, it is 0. So we've got that already. We go from 326.8 negative, add on 628.1. That brings you up to 301.3. And that'll be a second order curve. That 301.3 is offset by this, which brings me back down to 0. And then let's go ahead and label this. This is a second order curve. This is second order curve. This is first. And this is first. So in summary, the process was generate the free body diagrams and then treat each one as a separate beam, and when you are done, you have the total shear and the total moment diagram for the entire beam. That concludes this example. As always, it's an absolutely beautiful day for studying structure.